Welcome back everyone. Today looking at electrons and something we call electron configurations. So quick review here. We said that energy is quantized. What does it mean if something is quantized? So what this means for us is that it can only exist in certain values or quantities. So this kind of goes along with those Bohr orbits and saying that those electrons can only exist at those spots. So in the Bohr model, the further from the nucleus the electron is, the higher its energy. So just remember, further out you go, more and more energy that electron has. What are these electrons in the outermost layer called? Say this is what Lewis focused on. We called them valence electrons. These are important for bonding, for properties, things like that. Orbital. So think about, okay, quantum mechanical model. This is a region of space where an electron will spend 90% of its time. Those weird shapes. And then the four types. Remember, that's our SP, D, and F. Today it's going to be good that you remember where those are located on your periodic table, those SP, D, and F blocks. Alright, electron configurations, what we're here for today. Hopefully by this point you are thoroughly confused about why potassium and calcium did not follow that valence electron cheat that we used the other day. Well, we've been kind of lying to you a little bit, and we'll get into that in a second. So electron configurations, these are the way electrons are arranged around the nucleus. It gives us the actual order in which those are filled. So remember, each shape holds 2 electrons. Larger atoms have more orbitals, so they can fit all of those. It just kind of makes sense. If you have 2, you're not going to need that many orbitals. You're going to need 1 orbital. But if you have 50, you're going to need multiple. So electrons always fill the lowest to highest. But then this part right here, kind of these two things together, this is why the potassium and calcium didn't quite work for what we were trying to do. So 2 ways in which we know, or which we can predict how electrons are going to fill. The first is the diagonal rule, and it's simply like this. So if you take your, if you just take your paper, number 1 through 7, then kind of skip down, number 2 through 7, then skip down 3 through 6, 4 through 5, and then just start drawing diagonal lines through these. How this works is we always start here, and you just follow the arrow. So follow the arrow down. When you get to the end, circle back, and then you're here. Follow the arrow down, get to the end, and then you start here. And you just keep going with this, remembering that everyone in this column can hold 2 electrons. Everyone in this column can hold 6. The D column can hold 10, and the F can hold 14. So once you get to 2 in the 1s, you're full. So then you got to go to keep following the arrow down, go to the next one, which is here, and follow it down. Well, once you get 2 in that one, then you got to keep following these arrows down. So my numbering looks weird here. What I really meant was the P block can hold 6, the D block can hold 14, the F can hold, or the D block can hold 10, the F block can hold 14. It's not just those arrows, it's these columns. We'll see that here in a second. The other way is using your periodic table. So I tried to hint to you as we were doing the activity that the 1s, or that the S blocks hold 2. Hey look, 1s1, 1s2. The P blocks hold 6, P1, P2, P3, P4, P5, P6. So what these are the ending electron configurations for that element. So if you look at hydrogen, 1s1, it's full. If you go over here and look at oxygen, its last thing, for if you were to follow the diagonal rule, will be 2p4. But if you just count over, you could figure this out yourself. Careful here, these 2 really go up here. This periodic table just pulled them out to show you that we go D. Actually, that's wrong. We go F, then to D1. these F's are lower orbitals. We'll see that when we do an example. Alright, so let's practice. Give the electron configurations for these elements. So first thing you need to know is just how many electrons they have. Hydrogen has 1 electron. So if I'm following my diagonal rule, the first I run into is the 1s. And it holds up to 2 because it's an s orbital. But in this case, I only need 1. And then I'm done. Because I got my 1 electron. Helium has 2 electrons. So follow my diagonal rule. 1s is the first thing I fill, and it can hold up to 2. Well, 2 is already 2, so I'm done there. Calcium, a little bigger, holds 20, has 20 electrons. So this one, the first orbital I'm going to fill is the 1s. It holds 2 electrons. Well, that's still not to 20, so I got to follow my arrow, move to the next one. So the 2s holds 2. I'm still not to 20. Next orbital is the 2p. If I keep following my diagonal rule, 2p6 is the max it'll hold. I'm to 10, still not to 20. Okay, keep following my arrow. 3s2. It's full. Gotta keep following my orbital. 3p6. Okay, it's full. Still not to 20 though. And this is where your Bohr model kind of messed up. Is calcium actually puts 2 electrons in the 4s2 first before it would actually start filling the rest of the 3 orbital of the 3d. So this is where our diagonal rule helps us. The 4s is actually lower in energy than the 3d. So yes, the third ring does hold 18, but not before we put 2 in the 4s orbital. Kind of weird. That's why diagonal rule is your best bet. Next one, vanadium, 23 electrons. Well, we've gone up to 20 here, so I'm just going to copy my work. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and now I go back and fill that 3d. Holds up to 10. We only need 3 to get to 23. Iron has 26. What you're going to see is the exact same thing, except this 3d actually has 6 and pretty much copies it down. The last one there, Einsteinium, has a whole lot of them. Looking at the periodic table, 99 electrons. So this is going to be a longer one to do here. We're going to follow our diagonal rule a couple times, or look at our periodic table if you're using that rule. So 1s2, 2s2, oops, 2p6, 3s2, 3p6. I'm going to erase this, get out of my way here. After 3p6, we fill the 4s2 first, then we fill the 3d10. After the 3d10, we come back and fill the 4p6. Okay, still not there. So after the 4p6, we fill the 5s2. After the 5s2, we go to the 4d10. I'm just following my diagonal rule here, or using the periodic table, actually is what I'm doing as I look at it. So after I fill the 4d10, I then fill the 5p6. After the 5p6, like diagonal rule periodic table, I know I'm going to fill the 6s2 because that's the next lowest energy. After the 6s2, then I run into that F block. So F block is now 4f 14. I'm still not to 99. Got to keep going here. So after I fill the 4F14, now I'm back to the, got to think, 5D10. So see, you would have never predicted that looking at, you would have never predicted kind of these things here, looking at your Bohr model or anything like that. Always lowest energy first. Gets us some weird orbital configurations, but scientists have data to prove this and back this up, so we use it. All right, after the 5D10, we're now back to the 6P6. After the 6P6, we then go to the 7S2. After the 7S2, run into that F block again, and so now it's 5F. How many more do I need? I gotta count them. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. You can always go back and check yourself if you start counting. So 11 plus 2 is 13, plus 6, 19, 29, what is that? 43, 45, 51, 61, 63, 69, 79, 81, 87, 89, plus 10 more is 99. And if we go back and look at our cheat here, 5F11 is what we should have ended at. 5F11 is what we did. Alright, so notice you'll see that stinks to write every single thing out. So we do have something which is called the noble gas shortcut. So if you look at phosphorus, write its electron configuration out. What you do is you go up a row from phosphorus and all the way to the end to the noble gases. And what you'll see is the noble gas there on the end is neon. Neon ends in 2p6. So then you just copy the rest of this down here after you write the noble gas in brackets. Much, much shorter. So if we look at Einsteinium, kind of a weird one. Another hint is go find the noble gas that has it's really close to but fewer than your electrons. So Einsteinium had 99 electrons. So if I go to my periodic table and look, the noble gas with the closest number of electrons is radon, which has 88 electrons. You don't have to write that, but just a little note for me. And then write the rest of your electron configuration. If I go back and look here, radon has a ends in 6p6, so I just copy this part right here. 7s2, sorry, radon has 86 electrons. I just need to copy the rest of this. 7s2, 5f14. Much, much shorter for something like that. We could do these for the rest of them. I will let you do that. It's going to be part of our practice. But figured I'd just show it to you just in case you see that in the near future. We can also predict valence electrons from here. What you do is you just look at the highest orbital. So look for the highest number. In this case, it's 4. That's our only 4 orbital. So calcium has 2 valence electrons. If I go to Einsteinium is not a good case because it is ends in the F block. But to use that, what you do is find your highest number. In this case, it's 7. So highest principal quantum number is 7. It has 2 there. That's our best bet. Doesn't exactly work for the F block, but that's how you would do it. Find the highest principal quantum number, and then you might have multiple of them. But in this case, I only had one 7 orbital, and then count the electrons there.